and I'll hand it off to our first tutor.
Okay, let's see if I can, okay, I think I can share it. Okay, can everyone see?
Yeah, we can see.
Okay, cool. So I can't see the chat. Actually, I can. Okay, so if you ask questions in chat, I can see it now. So I'll be presenting on the environmental effects of PK and Van Hoff analysis. So the main equation to think about is the Henderson-Hasselbalch equation, which you might have been taught in general chemistry. So it's pH equals pK plus the log of the ratio of the deprotonated form divided by the concentration of the protonated form. So the pK is a value that depends on the chemical. So you can look that up or it's given. And then the pH value is something that you can manipulate by either adding like acid or base. But you can't really directly affect the ratio. So if you adjust the pH by 1, then the ratio will change by a factor of 10 because this is a log base 10. So any questions on that? Okay. So here's a chart I made with some of the common residues that can take different protonation states. These aren't the only ones. For example, serine is very important for nucleophilic attacks, but it has a pK that's like 16, so I didn't include it. So arginine, aspartic acid, cysteine, glutamic acid, histidine, lysine, and tyrosine. And here are kind of the base pK values. And here are the structures in both forms. So people often ask which one is HA and what's A minus. So I drew the structures here. Any questions? I can't see chat anymore because it blocks too much of my screen, so someone will have to say. Okay, so to kind of give an example, I'll use lysine, which has a side chain pK of about 10.5 normally. So if your pH is 7.5, then if you just plug that into the Henderson-Hasselbalch equation, you'll get that there are about 1,000 protonated lysines, the form on the right, for every one unprotonated lysine, which is the one on the left. So the equilibrium lies heavily to the right. So that's just kind of in a solution of just the amino acid on its own. And so let's talk about how being in a protein changes the game. So residues, since proteins are a polymer of amino acids, you have other side chains which can have an effect. So kind of think of it in terms of Coulomb's law, where the electrostatic energy is proportional to the charges divided by their distance from each other. So, and two like charges results in a positive energy value, which is energetically unfavorable. Opposite charges leads to a negative U, which is stabilizing because you want the lowest energy possible. So here are kind of the two example cases shown side by side. So you have the previous one where it's just lysine as an amino acid solo. And then on the right, you have a protein, an example protein. And in this one, you have a lysine whose side chain is close to an arginine. So arginine is another residue that takes a positive charge. So you kind of have in the protonated form, if you see on the far right, you have two positive charges in close proximity, which is energetically unfavorable. So this kind of imposes a penalty, an energetic penalty on the protonated form of lysine. So you can think of it as adjusting the relative energy levels. So now the protonated form is higher in energy and the unprotonated form is pretty much unchanged. So the protonated form becomes less favorable, which means that you won't want it to be protonated a lot. So more acidic because you want to lose that proton. So that means that the pKa will be lower. Any questions on this? Okay, I'll move on and cover kind of the same thing. So on the other hand, what if it's two residues that can take opposite charges? So it's pretty similar. And here you have glutamic acid, glutamate, and we'll just assume this is always negatively charged. So relative to kind of the base case of it just being a solo amino acid, if in the charged form, the protonated form of lysine, you now have a positive charge that is right next to a negative charge. So this kind of lowers the energy of the protonated form, which makes it more favorable. So in terms of pKa, a higher pKa means less affinity to lose a proton. So, and you want to be in the protonated form even more now because you have this electrostatic interaction. So the pKa will rise for this lysine. Okay, any other questions? Okay. So kind of the remaining cases, if you have two residues that can both take negative charges. So I'll leave you to think about this, but it's kind of similar to the two lysine case. So how would the relative acidities be for these two carboxylic acid groups? And to kind of make things more quantitative, here there is a journal article about this very phenomenon, and they actually measured the values. So you can see that the second column is kind of the base case, and then you have the average, and then the lowest among the ones that they measured, and then the highest pKa for the residue that they measured. So you can kind of see for all of these, the neutral pH is within all of the ranges for the residues. So depending on the environment, they can either be favored to be in the charged state or uncharged state. So there's a very large range. So now moving on to the Van Hoff equation. So we have these two formulas for delta G naught. You have delta G naught equals minus RT ln K, and you also have delta G naught equals delta H naught minus T delta S naught. So you can equate these two and then divide by negative RT, and you get the Van Hoff equation. So why is this useful? Well, you can think of it, you can treat it as a linear equation of the form y equals mx plus b. So your y value is your ln of k. Your slope is minus delta h over r. This could be a positive term or a negative term, depending on whether it's an endothermic or exothermic reaction. Your x equivalent is 1 over t, and your b or your y-intercept is negative s naught, delta s naught over r. And so by running this experiment at multiple temperatures, we can plot points, and then if we draw a line through this by plotting 1 over t versus ln(k), we can determine the values for the enthalpy and the entropy changes. And just kind of to give an idea of how much. Things vary if you change the energy. For every 6 kilojoules per mole, there is a 1 order of magnitude change in the ratio of the products to reactants. So here is a sample plot. So just kind of by definition, KEQ being greater than 1 means that the forward reaction is favored. KEQ being less than 1 means the backward reaction is favored. So if you just take the log of it, the log of 1 is 0. So now you kind of get, if the ln k is greater than 0, then that's favorable. ln k being less than 0 means backwards favorable. So if you kind of plot these points, and then you can extrapolate and find the y-intercept. I mean, you can't actually test 0 because that will require temperature to be infinite because it's 1 over T. And similarly, you can find the slope and use that to find the enthalpy change. And so you get these two regions where you're below the x-axis and above the x-axis, which isn't really shown well on here because the 0 point is this dashed horizontal line. But every temperature or 1 over temperature where you're below 0 means that the backward reaction is more favorable. And everywhere where your y value is positive corresponds to a temperature where the forward reaction is favored. Any questions? Okay, that's all I have. So I will stop sharing screen.
Hello, everyone. I'm just going to share my screen. Oh, can you stop your screen sharing first?
Yeah. Okay, should be done.
Can everyone see my screen okay?
Yes.
Okay, thank you. So I'm going to be going over protein folding and the hydrophobic effect. So this is the kind of stuff you guys addressed previous in class, but now we're going to be a little bit more quantitative with it and kind of use the mathematical tools you guys have been developing. So first, I just want to kind of address the complexity of protein folding, right? Because a lot of the times we think you just go from a chaotic polypeptide to a single well-defined native form. But this really isn't the case. There really is a lot of variability and diversity to the kind of proteins or states that form from the unfolded polypeptide. It's not just a simple, you have your polypeptide, you put it in solution, and here is your well-defined protein, right? So proteins have intermediate states. They have their native state, but they also have, let's say, these amorphous blobs, which like a lot of proteins don't have precisely defined structures so that they can interface with a lot of proteins. In addition to the complexity of the protein structure itself, proteins can aggregate with other proteins to form larger structures like these amyloid fibrils. So the point is, there isn't, when we say folded protein, there isn't just one folded protein. It's a lot more complicated than that. And these different types of proteins have different energies that we would have to consider. But in order to better understand protein folding, we can simplify our model, right? So we can just hand wave and say, for the sake of better understanding protein folding, let's reduce it to the case where we have an unfolded state with many conformations that's in equilibrium with a folded protein that's one conformation. This isn't what happens, right? But this is going to be good enough for us to study. So it's two states. And this is the premise that we're going to be using for the rest of our calculation. So what is it that we want to calculate? We want to calculate the free energy of protein folding, right? And by calculating this, we're hoping to understand what are the drivers of protein folding, right? Because as you guys understand, there's always a balance between enthalpy, the energetic component, and entropy, which is takes into consideration the number of configurations, the multiplicity, right? So what is it that drives protein folding? So when we go about doing that, we can let's just start with a simple expression for the standard free energy, right? So this is the expression we've been using, you guys have been using all along, right? This is nothing new. If we want to say what is the free energy of protein folding, that's equal to the enthalpy of protein folding minus T delta S, the change in entropy of protein. This is our first guess, right? We have to start somewhere. We might as well calculate this expression and see where it goes. And just to be a little bit more explicit, the change in enthalpy of the protein is the change in like the enthalpy of the interactions within the protein, and the change in entropy of the protein here is the change in the number of configurations as the protein folds. So in order to evaluate this expression, we need to first evaluate these terms, the change in enthalpy and the change in entropy. We don't need to calculate the temperature because that's just a property of the system, right? We can just arbitrarily choose a temperature. So first, let's calculate the entropy term, the change in the delta S protein. So in our simplified model, we said that we go from many unfolded configurations to a single folded configuration. So when we calculate the entropy of the protein, we can approach it as the entropy of the folded one minus the entropy of the unfolded one. And there's a lot of ways to calculate entropy, right? You guys have gone through a lot of different methods. You guys, the thermodynamic method with the heat and heat engines. There's the probabilistic definition, which you guys used in class. I'm going to show you here the statistical method because this is basically the exact same thing as a probabilistic method, but I can get into that a little bit later. So the change in the entropy of the protein in the folding process is the entropy of the folded protein minus entropy of unfolded. That should be pretty self-explanatory. So now we just plug in our R, ln multiplicity, right? But we can kind of multiplicity of the protein, we can kind of interpret that as a number of different configurations. So we want to calculate the number of folded configurations of the protein minus the number of, I put n sub c, which is the number of configurations of the unfolded protein. I just chose this particular labeling because that's what's used in the lecture, so it's consistent for you. But in our assumption, we know that, or we stated that there will be only one folded configuration. This is an assumption that we make. It's not true, but this is what we're going to say to simplify our calculations. So ln 1, that just goes to 0. So we're left with this minus r ln c. So this is what we have to calculate. How is it that we can approximate the number of configurations of the unfolded protein? So here, these are just diagrams from your textbook. Here we have to make additional assumptions. So we can intuitively think about the number of configurations in terms of the degrees of freedom of the polypeptide backbone, as well as the degrees of freedom in the residue. So just based purely experimentally, we can assume, or people did some calculations, and we can assume that there are 3 allowed configurations of a polypeptide backbone. Note that this isn't actually true, right? Remember that if you recall your Ramachandran diagram, that there are values of phi and psi angles that are allowed and values that are disallowed. But these are ranges, these are continuous. Here we just state that there are 3 allowed configurations. This isn't actually what happens, but it'll be enough for us to do this calculation. And for the amino acid side chain, same concept. There's a range of phi and psi values, or I mean, angle values for the residue, but we experimentally, they discovered or they conclude that it's enough to say for this calculation that we have 2 available configurations. But note that this isn't exactly true, right? So where does this go wrong? If you look at lysine, lysine's this long chain, right? It has a couple extra carbons and then the amino group at the end. That's going to have significantly more degrees of freedom than, let's say, the residue of a serine amino acid, right? So once again, just keep in mind that these are the sort of approximations that we have to make in order to do our calculation. So from this, how do we calculate the number of unfolded configurations? Well, if we have for a given amino acid, right? A given amino acid has a backbone and has a residue. The backbone can have 3 configurations or conformations. The residue can have 2 conformations. So the total combinations of backbone and residue is 6, just 3 times 2. And let's just say that our protein is, I'm going to choose an arbitrary number, 50 amino acids. So the number of different configurations for this protein is going to be 6 times 6 times 6, 50 times, which is the same thing as saying 6 to the 50th. So now that we've calculated the number of configurations, conformations of our protein, we can plug it back into our expression for the change in entropy of the protein, negative R ln n sub C, and then just plug it in, and this is the value we get. Does anyone have any questions up to this point? Okay, if not, I will continue. I can't see anything in chat, so if
I guess I do have one question.
Yeah.
For the 2, are we always, will it always be multiplied by 2? So like I get the 3 because of the Ramachandran, but then when you multiply it by 2 to get 6, is it always going to be 2? Are there like special situations where it wouldn't be 2?
Well, there are definitely many situations, right, when it's not 2. 2 is the approximation. We study, like, this is the set of amino acids. We have to somehow choose one number that kind of averages the degrees of freedom for all amino acids, right? We can't, it'd be too cumbersome just to calculate based on each amino acid. So this is just kind of an approximation. There are definitely like amino acids that have way more than 2 and amino acids that have less than 2. But this is just the approximation we use to consider all amino acids in their totality.
Okay, thank you.
Mm-hmm. And I kind of want to make a clarification because you brought up the point of Ramachandran diagram. The 3 doesn't come from the fact that there are like 3 regions in the Ramachandran diagram. It comes, it's just an experimental property that they did some experiments and we see, oh, we can approximate this using 3 conformations and it's reasonably accurate. Okay. Does that make sense?
Yes, thank you.
Oh, sure. So just to go back a little bit, this is our calculated value for the change in entropy of the protein. So if we go back a little bit, we've done this part. We know the temperature, we can just pick it. We just calculated the change in entropy. So now what we have to do is calculate the change in enthalpy. So change in enthalpy is a lot easier. Just experimentally, like we have to make another assumption. People did some experiments and they can ask, what is the average energetic contribution of an amino acid to the stability of the protein, right? So they did this. Of course, different amino acids have different energetic contributions to the stability of the protein, but they averaged it, they did some combination. The representative number is -3 kilojoules per mole per amino acid towards the stabilization of the protein. So using this, we can easily calculate the enthalpy, right? So we have -3 kilojoules per mole per residue, and we have 50 residues. We multiply together. This is the enthalpic contribution to the free energy of protein folding. And now that we have both terms, we can just plug back in. So we have the enthalpic term we just calculated from the approximation of -3 kilojoules per mole, stabilization per residue. The entropic term we used by calculating the number of configurations of the protein, and we get this value. But this is a large positive value, right? This isn't what we expect. If what this says is that protein folding is unfavorable. If protein folding was unfavorable, our biology would be messed up. We couldn't really produce proteins in any appreciable amount, right? So we know something is wrong. So what we have to think, what is it that we're missing? Well, if you think about it, right? If we put protein folding, it's not just a property of the protein. Protein folding is also a property of the system, right? Proteins fold in solution. So maybe for our next guess, we can consider the free energy of the water around the protein, the change in the free energy of the water around the protein as it folds. So if we want to consider that, right, we just add the free water energy, the free energy change of water to our expression, and we get this, right? And it has the exact same form as the protein form we used before. Instead of just the subscript being protein, we have the subscript being water. And now, same process as before. We have to calculate these 2 terms and use appropriate approximations that represent our simplified model. Does anyone have any questions about the addition of this component of the water consideration? Okay, if not, I'm just going to continue. So qualitatively, you guys have already encountered this concept, right? So when there are no hydrophobic molecules, water can form not only a lot of hydrogen bonds, but there are many ways to form hydrogen bonds. A water molecule can rotate in space and form a lot of, and regardless, there are many instances, there are a lot of rotations that allow hydrogen bonding. But if I stick a hydrophobic group, that severely limits of kind of the term the professor uses is freezes or rigidifies the number of orientations that a water molecule can have in order to have hydrogen bonding, right? So an introduction of hydrophobic group limits the number of ways hydrogen bonds can be formed. So also experimentally, we make a second assumption. First, we say that in an unfolded protein or water in bulk, right, when there are no hydrophobic groups, a single water molecule has 6 available low energy configurations, right? What this means is if I have a single water molecule, there are 6 ways I can orient it such that hydrogen bonding is satisfied. And again, this is of course a oversimplification assumption, right? Because water molecules don't exist in discrete configurations. There are rotation, a range of possible angles, but this is just for the sufficient for our calculation. And when you put in a hydrophobic group, you constrain that. So we experimentally discovered you only have 2 low energy configurations, right? So of the 6, you only get 2 configurations where you satisfy hydrogen bonding. So this, even though there's the limitation in that we're choosing discrete values where there should be a range of values possible, it represents the fact that when we put in a hydrophobic group, that the orientations that allow hydrogen bonding are constrained. Sorry, let me just reload this. My thing is not. Sorry, guys, a little technical difficulty. Give me a second. Can everyone see the screen clearly? It was lagging on my screen, so I can't tell.
Yes, we can.
Okay, thank you. So now that we've determined the assumptions, right? How many orientations a water molecule can have given different circumstances, we also need to determine the number of water molecules that interact with our protein, right? In order to determine the entropy, right? The entropy is related to the multiplicity and number of configurations. And that calculation requires us knowing how many water molecules are there and how many configurations are allowed per water molecule. So for our protein, we assume that half the amino acids are hydrophobic, half the amino acids are hydrophilic. We're going to ignore all the water molecules associated with the hydrophilic portion of the protein because those don't change, right? If you have your unfolded polypeptide, the water molecules are going to interact with them. When you have your folded protein, your water molecules still interact with the surface of the protein. There's no change. So we don't care about that because they cancel out when we calculate the difference of the entropies. What we do care about is the change in the interactions with the hydrophobic residues. So we know that based on our assumption, there are 25 hydrophobic residues, right? Half of our protein is hydrophobic. That's an assumption. Our second assumption is that when constrained, this is a separate assumption. Another assumption we have to make is that per hydrophobic residue, each hydrophobic residue interacts with 2 water molecules. That's just an assumption we make. That's experimental. There's no logic in that. So we have 25 hydrophobic residues. Each residue interacts with 20 water molecules. So we have 50 water molecules of relevance to us in a 50 amino acid protein. So once again, we go back to our statistical definition of entropy, right? So we want to calculate, 1, the entropy of the folded, and the entropy of the unfolded, and take the difference, and that's our change in entropy. So when our protein is unfolded, we have 6 to the 50th, right? Because there are 6 allowable orientations of the water molecule when it's not constrained by the hydrophobic groups. But when it's folded, there are only 2. So we have 2 to the 50th coming from the fact that there are 50 residues. And you calculate this out and we get an increase in entropy of this value. And this makes sense, right? When protein folds, the there's an increase in the entropy of water because the hydrophobic residues are being sequestered inside the protein. So now all we have to do is calculate the change in enthalpy of the protein folding process, and this is easy. We're just going to say it's 0. So why is it 0? Well, the number of hydrogen bonds doesn't change, and the strength of the hydrogen bond doesn't change, right? So I think a common point of confusion is that when I say the orientations are constrained for a water molecule, that doesn't mean that the number of hydrogen bonds changes. The number is the same, or approximately the same at least for our calculations. What changes is the number of ways we can reach that number of hydrogen bonds. The number of hydrogen bonds is the same, but the number of different ways that we can achieve that number of hydrogen bonds is different because hydrophobic groups constrain the water molecule. But since the number of hydrogen bonds doesn't change, the energy of the hydrogen bond doesn't change, the enthalpy of hydrogen bonding of water does not change. So now we have all our terms, so we just plug back in. Enthalpy is 0. This is what we calculated from our entropy of water. You get this. And now we put that back into our previous expression, right? So our expression before ignored this delta G part. It just had this G protein and we got this positive value. But when we incorporate the free energy change of the water around the protein, we get a negative value for the free energy of protein folding. And this is what we expect, right? It has to be spontaneous, has to be favorable in order for us to effectively produce proteins. So one thing I do want to point out is that what variable term is the hydrophobic effect, right? We've been talking really quantitatively about this hydrophobic effect, which is the phenomena by which proteins fold due to the increase in entropy of water. But the hydrophobic effect is very specific. It's the free energy change of the water surrounding the solute. That's this term. This term is the hydrophobic effect. When you add this into the expression free energy folding, this is what makes protein folding spontaneous. So this term is the hydrophobic effect. And for my last slide, I won't go over all of them with you because I already said them, but just to remind you, protein folding is a really complicated process, right? So we had to make many, many assumptions in order to get a value that makes sense, in order to simplify our model to understand what's happening. So I just listed all the assumptions we made here. So these are things that are just, we state as fact. They have a lot of inherent errors in them, but the estimations are close enough for us to understand what's happening. Does anyone have any questions? None? Okay, if not, I'll just hand it off to the next tutor. Thank you.
Okay. All right, so now I'll be talking about how we can analyze protein folding in terms of how we can experimentally look at some parameters of interest like delta H or delta S for the unfolding process. So first, I want to introduce this instrument and this process that you probably talked about in lecture. It's called differential scanning calorimetry, or DSC. And essentially, the reason why we're interested in this instrument is because if we have two samples that we run through the DSC machine, we can get information on what the heat capacity is of each of these samples. And through a series of calculations, we can then convert that to numbers that are of interest to us. So to kind of go over how this instrument works, consider these two samples A and B. So beaker A contains your protein of interest, whatever it might be, as well as some buffer solution that controls the pH, things like that. And in beaker B, you essentially have like the blank or the standard, which is everything that's in this beaker just except the protein. Because at the end of this instrument, what we're going to get is a heat capacity of sample A and a heat capacity of sample B. And if you take the subtraction, if you just do A minus B, then eventually you'll be left with the heat capacity of the protein, which is what we're after in the first place. And so some specifics on how this process works. Going into this machine, there are a few things that we already know or like the machine can calculate for us. So the first thing is the temperature of the sample. You see here that the DSC has a temperature monitor. So at any given time, we know what the temperature is inside the beaker. Additionally, we also know what the mass is or what the volume is going into these samples, because these are things that either we would measure ourselves or the instrument could measure for us. And lastly, one of our final knowns is we know the heat flow that's going into each of these samples. So because the machine is heating up these coils by flowing current through them, just by tracking the amount of current that's flowing through, we can kind of estimate how much heat is going in. And so to recap, if we know the mass of the sample, and we know the temperature and how the temperature changes over time, and we know that the amount of heat that was added, then all of this together can give us the heat capacity of the sample. And then because we have two heat capacities, we simply take the difference, and that gives us the heat capacity of our protein. And now, as we'll see, when you actually look at the output of the DSC, you get heat capacity at various different temperatures. So you don't just get one number output, you get a heat capacity at every temperature ranging from 20 degrees Celsius to 100 degrees Celsius, or however you choose to configure it. And so this is typically what the output trace would look like. You have a flat heat capacity that's very weakly dependent on temperature, because here you see that the heat capacity is kind of just flat, so it doesn't matter what the temperature is. It's basically the same in this region, except there's a little bit of sensitivity. However, for our purposes, we can say that this is almost independent of temperature. And then there's this middle region with this big spike, and then it levels off to another heat capacity that, while it is flat, it is still higher than the initial heat capacity. And these diagrams kind of show molecularly what's happening to the protein as you're going through this heating process. So first, if we start with region A, you see that this protein is completely folded here. So this is kind of like the native state of the protein. And you can see that for a pretty long time before it starts to unfold, it has a pretty low heat capacity. And the reason why it has a pretty low heat capacity is because if we're considering a protein as having a fixed folded state, it doesn't really have, or like at least the atoms within the protein don't really have a whole lot of freedom in terms of where they can move. And so as you're adding in more heat, the only way that the protein can kind of dissipate that heat is just through the atoms kind of vibrating. And so what you can think of this as it's similar to heating a piece of metal, because a piece of metal has a pretty low heat capacity because a lot of the atoms are kind of just locked into place. And so for that reason, if you like park your car outside on a really sunny day and you touch the roof of it, it feels pretty hot. However, as soon as you get to the point where the protein begins to denature, then that's when you start running into some differences in the heat capacity. So as soon as the protein first starts to denature, you start to see an increase in the heat capacity pretty sharply like this. And the reason for this is that now, in addition to the heat capacity, in addition to added heat making the atoms in the protein vibrate a little bit faster, it can actually go into a potential energy change, because now the protein has enough kinetic energy to just break free of its conformation. And as that happens to more and more of the protein molecule, as you see in C, you achieve the maximum heat capacity here. And this maximum heat capacity is pretty significant because it corresponds to the melting temperature of the protein. And the way that we define the melting temperature Tm is that this is the temperature at which half the protein is unfolded and half the protein is folded. And because we look at protein folding as an equilibrium process in which either you have a folded or unfolded state, this has some pretty nice properties when we plug it into the equilibrium expression. And then kind of just to round off the curve, you have section D over here, in which most of the protein is unfolded, but there's still a few remnants of it. And then finally, when you get to the last region, your protein is completely unfolded, and it is basically just a linear chain. And the reason why this still has a higher heat capacity than the original folded protein is that this linear chain, in addition to the atoms of the peptide itself being able to vibrate, this chain can itself rotate and go through all different types of molecular motion that kind of help to offload the heat that goes in. And that's why it has a higher heat capacity. Any questions so far? Okay, so next I'll go over a little bit of math that's relevant for deriving some of the parameters of interest. And a lot of this is in the lecture notes, but I just have one or two extra comments here. So first, here are some important definitions for enthalpy and heat capacity at constant pressure, and these come from chapter 6, and you can read about them more if you're interested, but for the purposes of this class and for this derivation, if you just assume these to be true, then things work out. And then what we can notice from this expression is that if we're interested in getting our dH term, what we have to do is just multiply the delta t onto this side and take the integral. And this is a pretty important step right here, because notice that we're looking at the heat capacity at constant pressure of unfolding, which is a very specific type of heat capacity in this process. And if we integrate this very specific heat capacity in this narrow temperature range from when the unfolding first starts to when the unfolding ends, then we'll get the delta H for the process of unfolding. So what do I mean by very specific heat capacity? Well, there are essentially 3 different heat capacities that are involved in the process, or at least what happens when we run a DSC experiment. So first, notice that based on whether the protein is completely folded or unfolded, that gives it a different heat capacity because that's the difference between region A and region E. And so if you start out over here where you have basically all the protein is folded, then you have the folded heat capacity. And on this extreme, you have the protein that's completely unfolded, so you have the capital U heat capacity. And anything in the middle is kind of just a mix of the two, and it's represented by this 1 minus F times F, where F is just a fraction of the protein that happens to be folded at that point. But there's also one more important heat capacity here, and that is specifically the heat capacity of unfolding. And the reason why we're interested in this heat capacity in particular is because if you're thinking about what happens in the process of the protein coming apart, of course, there is heat going into the system and the protein kind of moves faster. But what we're really interested in is the heat that goes into the protein and actually causes it to unfold. So specifically, the heat that goes in and causes a potential energy change. And that's what's represented by the heat capacity of unfolding, because the heat capacity of capital U just represents the unfolded protein kind of moving faster. And the heat capacity of capital F refers to like the folded protein kind of just vibrating in place. And so heat capacity of unfolding is kind of naturally the only thing that's left. And so if we continue with this, what we also know is that if we look at the equilibrium constant at this specific temperature, we know that this is going to be exactly equal to 1, because the equilibrium process that we're looking at in this case is the protein going from a folded state to an unfolded state. And so at the melting temperature, we know that the exactly half of the protein is unfolded. So basically it's a 1-to-1 ratio, which then allows us to say that delta G standard is equal to 0 at this very specific temperature. And that's a pretty important caveat, that this is only true at this particular temperature. And so with this knowledge, we know that delta G standard is defined in this way. And so this is actually right here, the expression that we're interested in at the end. Basically, if we're given a DSC curve, we know that we can take the integral of the heat capacity between very particular temperatures, and that gives us the delta H of unfolding term. But to get the delta S of unfolding, what we need to do is just take this delta H term and divide it by the melting temperature. And just one more time to reiterate the caveat, these delta H and delta S terms only apply at the specific melting temperature. And if you wanted to convert it back to, let's say, 25 degrees Celsius, there are 2 equations that you can look at in box 10.2 of your textbook that will handle the conversion. In my experience, I don't think you'll be asked to do that on a homework or exam, but in case, that's where you can find it. I think conceptually understanding this process is a little bit more important. Any questions so far?
Hi, do
Yeah.
we consider the hydrophobic effect here?
Hydrophobic effect. So in the process of protein unfolding, the only equilibrium that we're looking at is the protein going from folded to unfolded. And so kind of everything that's, we're really just looking at the protein stability itself. So I guess we're not really taking into account what
Well,
happens.
the hydrophobic effect is folded into it. I mean, you're not decomposing it into hydrogen bonds or covalent bonds. Everything that's going into the protein folding is included. So the hydrophobic effect comes into it. It doesn't, this experiment doesn't specifically dissect one contribution from another.
Okay,
You
thank
understand?
you.
Yeah.
Thank you.
Any other questions? Okay, so next, to kind of round out my presentation for today, the last topic I want to touch on is amyloid fibril formation. So you talked about amyloid fibrils in lecture just yesterday, but the first time that they were introduced in this class was actually in lecture 5 in slide 13. And to briefly recap what exactly fibrils are and why exactly they're a little bit of a concern in a biological context, is that the dominant structure or the dominant secondary structure that's involved in a fibril is this beta sheet. And if you'll recall, the beta sheet, if it's folded in this way, and if it's not in a barrel, and if it's just in a kind of straight planar shape, it has these hydrogen bonds on the surface that are kind of unsatisfied. And so the drive to satisfy these unmet hydrogen bonding needs kind of forces this protein to either encounter other unfolded proteins or loop-like regions of proteins that have already unfolded. And then it causes the formation of even more beta sheets. And so this is kind of a self-propagating process, because now even though the hydrogen bonds on this side of the fibril might be met by hydrogen bonding here, then on this side of the protein, you're going to have, again, more unmet hydrogen bonds, and that drives this to propagate by itself. And the reason why this is of particular concern is that in class, you looked at the protein folding landscape as just essentially proteins descending down a funnel. And even though you would expect that the native state of a protein, so this is the state of a protein that's functional and what we would normally associate with as a healthy protein, even though you'd expect that this is relative to other conformations, even though this is relatively more stable, it's not the most thermodynamically stable conformation a protein could adopt. Because if you look at the amyloid fibril right here, or even oligomers or amorphous aggregates, these are actually thermodynamically much more stable than the native state. And so protein folding is essentially a process of guiding the unfolded protein into this section here. But you can kind of view it as the native state is almost just kinetically trapped here, because if the protein had enough kinetic energy to escape this energy well, and if it were to end up becoming an amyloid fibril, then you would have a much larger problem on your hands, because then it would be much more difficult for the cell to overcome this energy well. And at this point, you would just have to hope that the fibril is degraded. And the formation of amyloid fibrils is implicated in the pathology of numerous diseases, Alzheimer's disease being one of them. And I don't know the specifics there, but I'm sure you can find many journal articles documenting why that is the case. And lastly, the last thing I wanted to go over today is this worksheet question. So this is getting at just using some of the parameters that you would obtain in a DSC experiment. So suppose you conduct a DSC experiment on a protein, and you say that you reach the maximum heat capacity at 75 degrees Celsius. And let's say that you determine that the delta H of unfolding is 22 kilojoules per mole. What is the melting temperature, and what is the standard entropy change for unfolding at this temperature? So does anyone want to take a guess as to how to maybe begin this question? Okay, I think we're running a little bit low on time, so I'll go ahead and go over the solution, and we'll post it later as well. So like we said earlier, the maximum heat capacity also corresponds to the melting temperature of a protein. So we know that Tm is equal to 75 degrees Celsius right off the bat. And this is the relationship that we found earlier in the slides. So then if we plug in these numbers and remember to use kelvins and not Celsius, then we can get that the standard entropy change is 63.28. 63.2 joules per Kelvin mole, and that is specifically at the melting temperature. If you wanted to convert it back to, say, at 27 degrees Celsius, you'd have to apply another formula. Okay, so that's all I have for today. Does anyone have any questions about what I talked about? Okay, so then I'm just going to stop the recording for now.